Good afternoon. Thank you all very much for coming to Lunch and Learn in this a little cold, snowy day. My name is Amin Kodai. I'm the chair of the EC department here at the Ritchie School. And it is my pleasure today to host here and introduce today's speaker, John McDonald. John is the Smart Grid Business Development Leader for GE's Grid Solutions business. He has over 45 years of experience in the electric utility industry. He has been active in professional society for years, including as the president of the IEEE Power and Energy Society, a member of the Board of Governors for the IEEE Standards Association, and VP of Technical Activities for the US National Committee of SIGRE, among many other roles. John has also been heavily involved in higher education. He has served as the vice chair and is now serving as the vice chair of the Texas A&M Smart Grid Center Advisory Board, and also a member of the Purdue University Strategic Research Advisory Council. John has published over 100 papers, 5 books, and has won US patents. He's also a registered professional engineer in California, Pennsylvania, and Georgia. John received his Bachelor of Science and Master of Science in Electrical Engineering, both in Power Engineering from Purdue and MBA from University of California, Berkeley. John is a Life Fellow of IEEE and was awarded the IEEE Millennium Medal in 2000, among many other awards and recognition, which I don't think I have enough time to go through all of that. Please join me in welcoming John.
I want to thank Amin and thank the university, for the opportunity to be here today. I grew up in Chicago. That's why I went to Purdue. So I'm used to a lot of snow. My wife and I, we've lived in Atlanta 34 years. And so I appreciate you guys bringing me snow today because I don't get it at home much anymore. So this is a real treat. I told Rajan this morning, I always want some amount of snow as we get close to Christmas. And now after today, I have all the snow I need, and I'm ready for Christmas, So this is a topic that, I've given 4 one-hour webinars for the IEEE Power and Energy Society. And this is session 4. The first one was Asset Performance Management. The second was Introduction to Distribution Management Systems. The third was Distribution Management System Real-Time Applications. And the fourth was this topic we'll do today, IT, OT, Information Technology, Operations Technology Convergence, which is very, very critical for utilities today, is bringing the operations group together with the IT group. These are groups that typically have very different cultures, and they traditionally have not worked well or very closely together. And enterprise data management. So this was the 4th session, and I told Amin just 2 days ago, I gave this as a webinar for IEEE Smart Grid to all the IEEE PES members in Africa, okay, just on 2 days ago. It had many, many questions from all over Africa on this topic, very interesting questions, okay. Amin talked about my background, and these are some of the key things we'll talk about. So I won't go through these because we'll touch on each of them, but there's trends that are very important because I always say that it's very important for us to have a balance between the work that we do and outside activities. In other words, internal focus and external focus. If you come to work every day and you do a good job with work and go home, you may not know what's happening in the world around you, which is changing very drastically and very quickly today with technology and standards. And you may make decisions for your company that are suboptimal, right? You may decide as a utility to buy equipment from a vendor, and that vendor hasn't followed the new standards being developed. And 6 months after you bought the equipment, it's obsolete because the way you communicate now is per a new standard that was just published. And that vendor didn't participate and didn't follow the standards work, okay? So it's very important that you have a balance between internal and external. That's why I talk about trends. We need to know what's happening in the world around us because we make better decisions for our organization. A couple things. One was smart grid. As we've transitioned from devices and systems, from microprocessor-based devices and systems to a holistic solution. At the universities, we teach students, don't just concern yourself with a microprocessor-based relay or communications box, but that has two-way communications capability today. It could be a node in a bigger network, right? A bigger system, integrated system. That integrated system has much more value to the customer than just that box itself, okay? So think of the big picture. At Georgia Tech in Atlanta, we have a systems engineering curriculum, and by system, we mean big picture, okay? Always think of the big picture. When I'm with a utility, a customer, I try to, make you think. I said, okay, you're talking about relays, you're talking about communications. Let's see how we can put these together into a bigger system that could provide more value to you. I want to show you examples of 6 integrated solutions that have the strongest business value to utilities. Success is technology, but also standards and policy. Interoperability today is very important. And the only way we can get different vendors' equipment to talk to each other is it has to comply to the same standard or set of standards. And policy is the strongest driver to drive a customer to buy equipment, the incentive. Why does Europe have so much wind generation? Well, beginning in 1990, countries passed policy to greatly incentivize investment in wind, all policy driven, okay? In the state of Georgia where I live, for the last 3 years, there was a $7,500 tax credit if you bought an electric vehicle. Well, that went away at the end of last year. You know what happened with sales of EVs? Dropped dramatically, okay? Policy is the strongest driver to incentivize. So I spend a lot of time with policymakers, but in the United States, it's very complicated because generation and transmission is governed federally, but distribution and the end-use customer is governed by 51 different public service commissions, 50 states and the District of Columbia, that are very different from each other, okay? Culture, we have to change the culture. We talked about this a little bit ago where technology for us is actually the easy part of what we do. Getting people to change the way they've been doing things for a long time and adopt something new is a challenge. So 2 things with respect to culture, particularly on distribution part of the grid. Closed loop control. We have to be able to accept the fact that once we test the logic, okay, we can let the logic act on its own without a human in the loop. And that's where we get what we call the self-healing grid, right? We detect the fault, locate the fault, isolate the fault, restore service around the faulted segment, all without a human interacting, okay? But it takes people to accept that after you've tested the logic. Second is distributing the intelligence. For many years, the concept of SCADA, supervisory control and data acquisition, was that all information would come up to the control center, be centralized, all the analysis decisions made, and then control commands would go down to the field equipment. We can't afford to do that anymore. It puts too much burden on the communication system, particularly with distribution, as we have devices on the feeders in addition to the substations, okay? So now we have intelligence at the substation level, and we have special grid edge controllers at the very end, on the low voltage network, particularly where we have a high penetration of rooftop solar panels. And I'll show you that in a minute. Much more emphasis on resiliency today, resiliency of the grid, which has caused much more attention to microgrids. It used to be that microgrids were a niche technology in 3 areas: military bases, university campuses, and rural villages. Our first microgrid project at GE was a rural village in British Columbia in Canada. But now, you look at the grid, instead of one heterogeneous grid where if there's a problem and it cascades, the whole grid could come down. We have very strategic microgrids that can operate on their own, islanded, or can be part of the big grid, right? Today we'll talk more about big data. Most of the application platforms today have cloud components, right? Now many, utilities are very concerned about their real-time data, their critical data, leaving their premises, okay? So a lot of utilities say, yeah, a cloud is okay as long as it's a private cloud within my premise. But no, these automation platforms, they use public clouds, okay? And it's inevitable, and that's the way things are going. And then social media. In the United States for a long time, utilities will key on your landline phone number when you call the utility to determine your customer record and your property address. So it used to be that all their customers had landline phones. This was before smartphones, right? Now with smartphones, very few people have landline phone numbers, but that's the system. We use the caller ID system, okay? So I wrote an article a couple of years ago on how we can use social media to accelerate the restoration of electricity after an outage. And what I wrote about was how we can use Twitter, and I'd rather have Georgia Power, who I buy power from, have my Twitter handle in my customer record. So then I can tweet outage information, and they look at my Twitter handle, bring up my customer record, know my property address, right? In the article, I went a step further and I said, I can show how we can intelligently keyword search and parse the information in the tweet, extract the outage information from the customer with no human involved, and put it in the outage management system, okay? So we need to move from landline phones more to social media. What's very important is the convergence, as I said, of information technology and operations technology. One very important concept, and this actually was a consensus of all the industry experts at NREL, a workshop where I presented a couple of years ago at NREL. It was an ADMS workshop, Advanced Distribution Management System. When a utility buys a new SCADA system for distribution, an Advanced Distribution Management System, the total project cost, if done correctly, 30% of the total project cost is the cost of the system from the vendor, but 70% of the total project cost should be the cost to integrate that ADMS with a number of other systems around their enterprise. And how well they do in integration is directly proportional to the resiliency of their grid. Okay, how many outages do they have? If you're a customer on that system, how long your outage is, right? The duration of your outage. And then the last point, which is very important here, is before we think about a smart grid, adding all kinds of new stuff to the grid, we need to make sure we have a strong grid, right? Strong grid before smart grid. You wouldn't build a house on a foundation that had a bunch of cracks in it, right? You want to make sure you have a strong foundation before you start adding new stuff. And a strong grid is the communications infrastructure and the IT infrastructure. If I add a bunch of new applications and I have a communications infrastructure that isn't robust in certain areas, I won't get the full benefits of the new stuff that I've added. The response requirements may not be met, the bandwidth requirements, and I may have too much latency or delay in my application. So these are really some key trends. We want to bring IT and OT together. Okay, that's bringing electrical and information infrastructures together. We can improve the reliability, operational performance, and productivity, and increase energy efficiency and decrease carbon emissions. But also with Smart Grid, we're empowering consumers now to manage their energy use and save money without compromising their lifestyle by helping them implement in-home energy saving technology, okay? That's very new with the end customer. 10 years ago, we started a new organization in the industry called the Smart Grid Consumer Collaborative. I've been involved with for 10 years, and we do research and education on the end-use customer part of Smart Grid. What's the value proposition to the end-use customer, which is different than the value proposition to the utility? And then a big challenge has been optimizing the integration of renewable energy, the transmission level, the distribution level, and end-use customer. So bottom line is, with smart grid, much more focus on the distribution system, okay? And why is that important? I'll give you one example. We have 52,000 distribution substations in the United States, but only 2/3 of those today have any automation installed, okay? 1/3 of these are unobservable at the utility control center. So if your home is connected to one of those and you have an outage, the utility doesn't know you're out until you call them, okay? So for years, we've invested in transmission and generation. We haven't invested in distribution. So one of the biggest, pluses here with smart grid in the last 12, 13 years is much more focus on distribution. So I call this the smarter grid because in my career, I've been adding intelligence to the grid for over 45 years, okay? So smart grid, the concept of smart grid isn't new. The question is, what are we doing in the last 10, 12 years that's different than what we were doing before? And that's highlighted in light green, okay? So I like to differentiate the smarter grid, which is the new stuff that we're doing, okay? And we're doing voltage control, but we've been doing it before because it's directly proportional load. If I want to manage the load in the summer of a summer peaking utility, if I lower the secondary voltage, I lower the load. But today what we're doing is we're integrating voltage control with reactive power control. We call it integrated volt-var control, which has more benefits to the utility. We talked about renewables. We're adding more sensors to the grid, and we're adding more specialized sensors. So there's a lot of work going on in power electronics, right, for new applications of power electronics. They're giving us new insight into different parts of the grid. This sensor here can detect a number of gases dissolved in the oil of the main tank of the transformer. And if I see a certain gas, like methane or ethylene or acetylene, it's generated by a specific failure mode that's occurring in the transformer. I know exactly what's causing that gas, okay? So we call it DGA, dissolved gas analysis, is extremely important to predict the health of an asset, okay? And we have sensors today that can detect up to 9 different gases on a continuous basis in the oil of the main tank of the transformer. We'll talk today, the focus, strongest business cases on distribution management and distribution automation. Distribution management would be the SCADA system in the control center. Distribution automation would be downstream of the substation. And then smart meters. We'll talk more about that. This is some of the characteristics of the old grid and the new grid. The old grid, you called the utility when the power went out. New grid, the utility knows the power's out and usually restores it automatically. Okay. So you want to be buying power and be connected to utility is much more proactive, right? If you call the utility and say your power's out and they say, really? Look to your neighbor. Is your neighbor's house dark? Look to the other neighbors. Look across the street. Utility doesn't know that. They're relying on you to give that information. I want to call the utility, and the utility says, yes, we know, right? And we know the piece of equipment that is causing the problem. We have a crew there replacing it, and your power should be restored within 2 hours. And we will call you in 2 hours to make sure. I feel much better, right, as a customer. And that's a result of utilities doing a better job with distribution management system, outage management, geographic information system, smart meters, and integrating all of this together. So communications is foundational. We have the electrical infrastructure, the power equipment, renewables, sensors, but communications ties everything together, right? I say communications is the enabling technology that allows us to automate. So when I was at the university and studying power engineering for bachelor's and master's, I quickly realized I love automation of the grid, but I quickly realized I need to learn a lot about communications because I can't automate the grid unless I have lots of different types of communication technologies, okay? I need to know a lot about it. And it's really foundational. This is the physical equipment on the grid, but this is the different communication technologies. It's a hybrid infrastructure of different technologies, and the differences are wired versus wireless, right? Microwave, wireless, fiber optic, wired, and public versus private. Did the utility build it and they own it? Or are they using a public carrier, right? So every step of the way along this infrastructure of their service area, they have these decisions to make, these trade-offs, okay? Typically when we need high reliability and high throughput, many times we go to wired, redundant fiber rings. As we go out and we go to distribution, our communication needs go from point to point to point to multi-point. The transmission generation, it's point to point. Fiber makes sense. Get out on distribution, now we need to blanket a large area with communications. You don't do that point to point. So it's wireless, 950 megahertz UHF communications is what we use, particularly with distribution. So you have to look at every part of the service area and say, what's the best technology? Whoops. And then we have the data services and the applications. So think of this. You don't want to be adding a bunch of new stuff here if you have weaknesses down here, right? Because you're throwing money away. You won't have the benefit, the full benefits. You've got to look at this first. Make sure it's strong, okay? So these are the 6 solutions that we felt about 10, 11 years ago had the strongest business cases for electric utilities in general. Asset optimization. First look at critical transformers, the data from critical transformers and the analysis of that data. Now we've moved from transformers to high voltage and medium voltage circuit breakers. Demand optimization. We can aggregate customers' load and use it as a dispatch tool in the control center. Many times it's cheaper to use aggregated demand than it is to ramp a generating unit up, okay, or down. Smart meters and communications, distribution optimization. Today, for every dollar we invest in distribution optimization, we get about $5 to $6 back. So the benefit to cost ratio is about 5 to 6 to 1, and the payback period is less than 3 years, typically. By far the strongest business case, investment in distribution. Second would probably be asset optimization today. Then we get into the transmission part of the system. A lot of work going on today on synchrophasers. This is a new data source here. SCADA data is every 2 to 4 seconds. But with synchrophasers now, we're getting a data value 40 to 50 times per second, which gives us a lot more insight into what's happening on the grid. And we're now, looking at all the different ways we can get value from this new source of data, okay? And then workforce and engineering design optimization. We really need to focus on the workforce because in the United States, in the next 5 years, about 40% of the employees today and about 60% of the executives will retire. So we really have, we need to attract as many young professionals as students and young professionals into power and energy because there's tremendous demand today of the workforce and not enough supply. So you see things like signing bonuses from companies. When my son graduated from Georgia Tech in 2007, he had 4 different internships as an undergraduate, bachelor's degree, took 2 power courses, and GE and Commonwealth Edison in Chicago bid on him and kept upping the signing bonus to attract him to come, and he eventually signed with GE and got a $9,000 check in 12 years ago to join GE. So the demand is strong, but the supply is not enough. Okay, we need more and more qualified. By qualified, I mean taking the right courses at the university and having as many different internships and work experience as you can. Okay, so if we take these 6 and we have a technology architecture roadmap color-coded, this is what I mean by an integrated solution. So part of the Internet of Things is bringing computers together with big data and analytics and connectivity. Connectivity is bringing it all together with communications so the data is readily available. Look at this in terms of the light blue boxes. Here you have, this is the office or control center. This is the substation. This is the feeders from the substation. I have blue boxes here, software applications, systems, microprocessor-based devices from different vendors. All need to be integrated and communicate with each other to form this integrated solution, okay? And this isn't trivial. Getting different vendors' equipment to communicate successfully with each other, even though all the vendors say we're compliant with that industry standard protocol, typically doesn't work the first time. But when this integrated solution here has tremendous value, the light blue boxes are the distribution with a benefit cost ratio of 5-to-1, okay, very strong. With standards, the challenge with standards has been that there's hundreds and hundreds of standards available. So from an industry point of view, you say, okay, I'm interested in this part of the grid. How do I know which standards apply to the substation, this substation component, or the control center? So from 2010 to 2015, I chaired a board of 25 industry experts called the Smart Grid Interoperability Panel. We're responsible for all the smart grid standards work for the United States, funded by NIST initially, which is part of the Department of Commerce. And we looked at all the hundreds of standards and we said, we need to help the industry. These 16 standards here are foundational to smart grid. So we said, we need to help the industry. It's not, no one can go through hundreds of standards and figure out, what to use. But if we can narrow it down to a small number, it makes it a lot easier. So these 16 here are what I call the foundational standards for smart grid. They cover generation, transmission, distribution, and the end-use customer. Cybersecurity, synchrophasers, software applications, everything. Okay? And what makes it easier today is worldwide there's one industry standard for one control center to talk to another control center called Inter-Control Center Communications Protocol, ICCP. From control center to the field, there's 2 protocols worldwide. One is predominant with North America called Distributed Network Protocol 3 or IEEE 1815, and one is predominant with European suppliers. And then within the field, the worldwide standard is what we call IEC 61850. And then we also use DNP3. So there's a much smaller number worldwide to consider today, okay? So as we get into Internet of Things and looking at integration of computers and devices, the 2 key words, integration and interoperability, there's 5 key components that every utility must invest in and keep up to date. Smart meters, the AMI metering communications and the data from the smart meters, geographic information system, outage management system, and distribution management system. Those 5 are key to the utilities managing their distribution system. And smart meters not only give us meter readings, but we get the voltage from certain smart meters at the ends of certain feeders to make sure the voltage is above the industry standard that says the voltage at the customer must not be less than 114 volts. And we also get, when you have an outage at home, the meter has enough energy to make one last communication to the utility to report that outage, called last gasp communication. The geographic information system has all the digitized maps of the service area of the utility and a facilities database of every asset. And that's the reference system for the network model. The distribution management system, we take all the status changes and send them to the outage management system. So I'm showing you different ways of integration that really provide value when we integrate all these systems together. And we want to move customers from using phone to social media, okay? So, Internet of Things, how do we leverage this, right? At GE, for instance, how do we leverage this with products we're developing, right, to help customers do a better job with their organizations. So we're talking, as I said, intelligent machines together with big data and analytics and connecting with people at work, connecting people any place, any way, and any time for intelligent operations. There's a lot of focus today on big data and analytics to the point where we're identifying new data sources that we haven't had before, new sensors and things, but particularly new analytics that provide new value streams to the customer that they've never had before. And I always say, when we benchmark best practices, we traditionally benchmark only within our own industry. And we need to be more creative, and let's look at best practices outside our industry. Enlarge our thinking, because these are some areas that are very new to us in the utility industry with big data and analytics. And we're doing a really good job now working with customers and thinking outside the box and looking at new value streams. So what this does with analytics, it gives us opportunities, as I said, to think outside the box and look at new areas of analytics to provide value that we haven't had before. Could be insight into metering, using the meter data to a greater extent, outage, reliability, and in reliability, one of the questions I got from Africa Tuesday was going into more detail with life cycle analysis and portfolio optimization with reliability information, renewables insight. And this is new for us with Smart Grid, is engaging the end-use customer. We had never done that before, okay? And insight into consumers. So this is all new with big data, analytics. And then when we talk about data, what's very important is, for years in our industry, the way we did supervisory control and data acquisition, or SCADA, was our only focus was getting data from the field and bringing that data up to the operators in the control center to monitor and control the grid, okay, only. Because the equipment we had in the substation was called an RTU, a remote terminal unit, and it was designed for hardwired I/O. Every single point had wires that went to the RTU to a terminal strip, analog points, digital points. We processed that data and we sent it up to the control center. And it was at the scan rate of the SCADA master. So it might be every 2 seconds or every 4 seconds. All of a sudden in 1984, we have the first microprocessor-based relay that was introduced to the industry. This was revolutionary because all the devices up to that point were standalone, no communications. And if you wanted to read the device, you had to go out to the field to read it. Now in '84, we have the first microprocessor-based relay with two-way communications, okay? And through the rest of the '80s and the '90s, more and more vendors now are supplying these new microprocessor-based devices. These have data for the control center, like the RTUs, but they have a new source of data that we had never used before. And that was data not for the operators, but for other groups in the utility, which could be maintenance, power quality, asset management, okay? So we were managing these new microprocessor-based devices as we did with the previous equipment and only focused on operational data. In other words, we weren't getting the full value from $5,000 or $10,000 for a microprocessor-based device. So I said we need to look at the different types of data and manage them differently. So in 2003, I wrote an article in IEEE Power and Energy magazine that introduced the concept in 2003 of operational and non-operational data. So operational data is what we had been focused on before with intelligent electronic devices, or these microprocessor-based devices, information for the operators in the SCADA system. But the new source of data here is the non-operational data. So the operators aren't concerned with this, but as I said, other business groups in the utility are. And in projects I've done, we've found maybe 25 to 30 other groups in the utility that could benefit from this data And if they had the data, they could provide more value to the organization through their applications, okay? So the primary user is someone other than the operators. So the lesson here is with data, is you really have to understand the data, right? The sources of data, but more importantly, who can receive value from this data in the organization, right? You know, who can receive value? And make sure that there's a mapping between all the users and their data needs and all the data sources throughout the enterprise, okay? And I mean this. Typically today, the way electric utilities have implemented microprocessor-based devices, at best, they're getting no more than 20 to 30% of the potential benefits of their investment because of the way they've implemented and architected that device in the field. Much less than 50%, okay, in general. So the focus today is on this type of data. This data is not just points, but it's files also. It could be a digitized waveform from a relay, or it could be a sequence events report. So it's you know, points and files. And the operational data is time sequenced, real time or near real time. And typically we use standard protocols to communicate that. Non-op data is points or files, typically historical and on demand. And we may need a vendor-specific proprietary format to extract the file, okay? So we need to characterize these and manage these differently. Only then do we get the full value, full return on investment. So the situation today with most utilities, and I've been doing projects in this area for almost 20 years now, and we have made very little progress. And it's not so much technology, but it's culture. It's because all the organizations, you know, every organization, we work very siloed, right? Your group, the group that you're in, typically has its own data, its own applications, and you're incentivized to do well within your group, but you're typically not incentivized to do well across other groups, okay? So you really focus on your own needs. And so that's what happens here. This is the systems of each group, the devices of each group, the existing data repositories, databases of each group, and with no sharing going on, siloed, okay? And what the target here, what we want in the IT infrastructure is more of a federated data mart here on the IT side that brings together all the systems, all the devices, and all the repositories, and make sure we satisfy the data needs of not only the operators in the control center, but all the other business groups within the organization, all the non-op users. And these, as I said, there's 25 to 30 or so different groups. So this isn't trivial. The goal then would be, we have standard architectures in the field that give us the ability to extract the data that we've identified, concentrate it, send it out into the enterprise, so we can bring it over to the corporate network, so that in cyan here, we have all the data sources in the enterprise, and in green here, we have all the different users that now are getting the data that they need and providing the most value they can to the organization. And we're truly now getting all the benefits of the investment and all the data sources that we've made, okay? So one thing that's very important with data is when we talk about renewables, is having data coming back from a wind farm or from PV panels, right? Because utilities, when you start with like microgrids and distributed generation, if you don't have enough data coming back, you have things happening on your grid and you don't have full information about that, which means it's difficult to manage, right? You can't even manage it. So the difficulty here is data, but also the difficulty is in distribution. For instance, we designed the distribution system originally, assuming electricity flowed in one direction from source to load. And now when we connect distributed generation to distribution, we have electricity flowing in two directions. Used to be, if I was a field worker, I'd go out to the distribution system and I'd open the upstream device, and I knew I had a safe working situation. It was de-energized, right? That's not true anymore, right? Because you have distributed generation now connected all across the distribution system. So distribution controls and protection was traditionally took advantage of and designed for one-way electricity flow. So we have some challenges today. We have protection ratings not match the fault currents, because when a fault occurs, we not only have the contribution from the source, but we could have a load side contribution from the distributed generation. But what complicates that is that load side contribution varies because the sun doesn't shine constantly all the time. The wind doesn't blow constantly all the time. It's intermittent, right? So that load side contribution to the fault varies. So how do you set your protection relays? As the penetration of renewables grows, your load side contribution to a fault grows, and you've really got to take that into account in protection, okay? This is a microgrid that was installed in a rural village in British Columbia. So it's just an example of a village having hydrogen fuel cells and hydro generation, some PV panels, and their base generation was diesel. And they had residential and industrial load. And we needed to manage that microgrid where to minimize the diesel generation, because it emits CO2, the atmosphere, maximize the use of the other distributed generation, and meet the load requirements. So we took a microprocessor-based relay here and added logic to that to be a microgrid controller. And then these blue boxes here are high-speed communication boxes that tie everything together. Okay? This is a new family of devices. It's a new application in power electronics called Low Voltage Network Dynamic Grid Edge Controller. So we're implementing these now it could be outside your home. So if your home has rooftop solar panels, and a lot of your neighbors do, what happens is there's a lot of volatility on the low voltage network because of the intermittency of the sun, right? When the sun is behind the clouds, none of those homes are generating. All of a sudden the sun comes out from the clouds and all of those homes generate instantaneously. So the voltage on that feeder spikes and oscillates, right? So the volatility creates a lot of problems. If you think about it, all the controllers we use on the grid have been mechanical controllers. Think about a load tap changer in the substation. 33 positions, 16 raised, 16 lower, a zero neutral position. It's mechanical. The more that operates, its lifetime, expected lifetime decreases, okay? So the more volatility on the grid, the lifetime of these mechanical controllers is drastically reduced. So we need to mitigate, we need to attack that volatility where it's introduced into the grid, which is on the low voltage network. So I looked at, this is an article I did back in 2013, and I looked at there's San Diego Gas and Electric had a feeder where over 35% of the homes on one feeder had rooftop solar panels. That's a high penetration. And the tap changer in the substation is designed so that no matter how the primary voltage fluctuates, you want to keep the secondary voltage constant, right? You want the voltage at your home to be constant, otherwise your light bulbs will be real bright, real dim, real bright, real dim. So this changes taps. Before any of these homes implemented rooftop solar panels, tap changer was operated about 5 times per day, lifetime of 35 years. Now, with 35% penetration, this tap changer is operating over 100 times per day, and its lifetime is less than 2 years. Okay? This is a real challenge, because the grid in time is going to be more volatile as more and more renewables are integrated, and mechanical means of control don't make sense. So this is why universities, power electronics researchers and power electronics expertise needs to work more closely with power system applications, power system folks, because I wrote this for Power Electronics Magazine, and I said there's new applications of power electronics because of the changing grid, okay? Online tap changers, low voltage network dynamic grid edge controllers, and smart inverters, just to name a couple, okay? Now, there's new sources of data, and this is what we find is, as we develop new analytics, big data, and integration, we're getting new sensors and we're getting new sources of data. Very appropriate to be in Denver and talking about this because the most progressive utility in the United States with unmanned aerial vehicles is Xcel Energy, real pioneer. With robotics, it's Hydro-Quebec. So I've studied this for about a year and a half, and I did an ad hoc survey. I said, okay, from UAVs and robotics, we have different types of data. We have photography, we have imagery, LiDAR and FODAR images as sources of information, and infrared sensors. We can see hotspots, right? Utilities use this data for asset management in the geographic information system, outage management system, and a new set of applications we're developing, like for Commonwealth Edison in Chicago, is storm damage assessments. Okay, you can prepare for the storm and do assessments after the storm. So I said, okay, how is this data being used? Because we're in the infancy right now of using UAVs and robotics. And it turned out some utilities are having humans watch hours of streaming video to detect potential problems like conductor wear or corrosion. And I said we need to pursue an automated image analysis. So here's a research, here's a field where how can we automate image analysis to look for the potential problems, right? So create value with automated image analysis. It's just not practical or beneficial use of resources for humans to have to do that. Okay, so that's one area that's a focus today. So I did this brief ad hoc survey in late 2017 with utilities, consultants, and power industry consortia. I wrote an opinion editorial last year for T&D World Magazine that was called Drones and Robots, a Data Management Opportunity. Okay? Because what I found was a coordinated industry response to the emergence of UAVs and robotics can speed time to value. We don't have that right now. It's really a shotgun approach. So I said, power utility use of UAVs and robotics is in its infancy. They're an effective, though, and efficient means to monitor infrastructure health and perform remedial work. So the value is there. How raw and analyzed data is stored, routed, or otherwise made available across the utility organization is different. There's no standards. It's very, very different for each utility. And typically very siloed. So not all groups in the utility that need this information are getting it, okay? So my recommendations are de-silo the utility and its approach to data management. And let's get organization-wide value creation that creates a positive business case for new technologies and makes a power utility more nimble and competitive. So it's one thing to do data, it's one thing to create analytics, but if it's only being used by one small group in the organization, you're not getting the full benefits, right? Organization-wide. So de-silo the utility. Have a holistic approach, okay? So we finished a book last year, a new book. It's called Big Data Application in Power Systems. Okay, a brand new book published by Elsevier. Okay, Big Data Application in Power Systems. And I wrote the first chapter of the book called Becoming, or a holistic approach, means company-wide, not individual group, but de-siloed, a holistic approach to becoming a data-driven utility. How an organization can be driven by data to get the full benefits of that data. So these are recommendations. De-silo. Now is the time to apply this holistic data management thinking with UAVs and robotic outputs for value creation. The power industry, we should determine and pursue common requirements and push the purveyors, the folks that are doing it, to comply with them. Because we don't have any standards right now, no standard approach. We need to adopt standard data formats and data analytics based on open source architectures and true enterprise-wide integration of the information. When something is in its infancy, now is the time to do it. It's much easier to do it than when it's more mature and people have standardized a certain way to do it. But the real pitfall here by customers is they will want something immediate, right? Some solution right away, and they'll team with a vendor and use that vendor's proprietary approach. They'll get locked in to one vendor. That's the worst thing that a customer could do. Avoid proprietary solutions that limit the utility's future options. You're captive to that vendor, they can charge you whatever they want, and they may not be developing the best technology that there is, okay? So that's the prepared material on this subject. But I'd be happy if there's any questions or comments. Especially for those of you that might be working in some of these areas. Be very interesting. Okay. Anybody have any comments or any questions?
Question. So, let's say you're an engineering student and you're studying electrical engineering. How important do you think it is to get computer science skills? It seems like a lot of what you're talking about is very computer science oriented.
Yeah, no, it is, and that's why we at GE, as well as many electric utilities, we're hiring data scientists for the very first time. We formed a new GE digital business that's now called NUCO. And we combined GE Power Digital from our power business with GE Digital in general, but with the software solutions business, which is all the SCADA systems from Grid, that's all now one new business, which is digital. What we find though is when we hire the data scientists, they're very good with data science, but they have no knowledge of the power system. So I would say a dynamite combination today that would really be in demand. If you have data science background and familiarity with the grid, few and far between. So we, originally our GE Digital CEO we hired from Microsoft. 25 years at Microsoft. He led the cloud platform, the Azure development of Microsoft, came in, and he was a fascinating guy because the more he learned about the grid, he looked at the grid now from a whole different perspective than those of us that grew up in power. And it was phenomenal. I mean, it was fascinating, his perspective from a Microsoft and data science perspective. So as he learned more about the grid, it was really, really valuable. So I'd say if you can come in and have some of that already, but the data science need is growing. We've applied data science now to asset performance management. We've moved from reactive maintenance of assets to predictive. Instead of waiting until something failed, let's look at the health of it on a continuous basis and the risk of that asset and manage that, right? Preventive failure. And to do that, it's artificial intelligence, machine learning, and the concept of a digital twin. So we take the physics of the asset, the behavior of it, and we model it digitally, and then we use that digital model. And this is all driven by data science. But if you don't have the knowledge of the power system, you look at this asset, which is a transformer, a circuit breaker, and you don't have a feel for what it's doing. So to me, we see pure data scientists or pure power system people, but not a combination.
Increased use of PRs. Do you think that PhD folks change
peer-to-peer exchange of power. In other words, buying electricity. Yeah. I think, so buying, customer to customer buying, so I think, to me, I think that's pretty far off, if ever. I think, to me, I think the next step might be like they do in Europe, is, you know, we have, for transmission, we have independent system operators that do regional control, transmission owners underneath them. John Wellinghoff, when he was chairman of FERC, he was a proponent of the concept of a DSO in the United States, the distribution system operator. So to me, the more possible next step might be, as we get down to the end use customer, is look at regional management of distribution. So like we do with transmission and generation, do that with distribution. And then I think if that happens, then I think you work your way down to the end use customer. But the thing that's would hold us back from like transactive energy or doing stuff like this is the communications infrastructure. You know, if you, for instance, if I put logic at the substation level, and I have an application that's running at substation level, and I want the decision making to occur at that level without going up to the control center. To make the right decision, I may need information from the neighboring substations, the peer substations. I don't want to have to go up to the control center to get that and come back down. What I need is peer-to-peer communications. Okay, so to me, the challenge today is, as a utility, is having a communications infrastructure, so when I distribute the intelligence, I can do more decision making downstream, but I may need more data, which means I need not just up and down communications, but I need more peer-to-peer communications. That would enable me to have the data that I need, so I don't have to go upstream. I can do more decision making at the different levels of the hierarchy. Okay, so I think DSOs would be the next step, but I think we really have to think about the strong grid, the communications infrastructure. That's key, you know. Okay.
5 solutions that you had, holistic solutions for smart grid. We had optimization in 4 of those, like
Right.
asset, demand, transmission, distribution. What is the role of optimization? Because that's one of the topics that we don't focus on much in engineering, but we use it a lot. So what are the applications? How do you see that would play out?
I think, you know, it's, I mean, the focus of optimization is, you know, is looking at the existing situation first, and then saying, you know, could I improve this existing situation? But then the next question is, do I have all the data I need to do that, right? And that's why all the utilities today in the last 2 years have started something that's very new, and it's called an observability strategy. So part of optimization is, do I have all the data I need, right? And most utilities, I said, don't. There's pockets of unobservability. So an observability strategy, which is a very new term in the industry, utilities are really looking at their entire service area and saying, do I have enough data coming in from all the parts of my service area, you know, that I need data from, right? And then the next step is, I have the data now, I want to optimize. I want to do the best I can. So what analytics do I need? And that's the focus today, is all the different possible value streams. And there's many, many different optimization, there's many different ways to optimize, whether it's transmission or demand or distribution, but it all relies on data and analytics. That's why what we're doing with data and analytics is so critical today. Because in most cases, we don't have all the data. In many cases, we don't have the communications infrastructure that we need. And in many cases, we don't have the analytics that we need. So it all comes together into, and I always say, you know, in an ADMS, we have a lot of powerful applications for distribution, but you can only optimize what you know is happening. If you don't have enough data coming in, you have all these high-powered applications you paid for, but they're not able to do the optimization. There's not enough data from substations, and there's very little data coming from feeders, right? So if you truly want to do optimization, you have to have the data you need to optimize. And so that's why observability strategy is a huge focus today. You know, what data do we need? What data don't we have? And let's make sure first and foremost we look at data, and second, analytics. And a third part of this is dashboards, right? Because every different group in the utility wants to see different data and present it in different ways. So we have to have the ability to put together flexible dashboards so each individual in each group can see what they want to see. Like Commonwealth Edison is very good, where you look at, in Chicago, each of the, whether it's an executive or whether it's asset management or power quality, whoever it is, there's certain data that they want to see and present it in a certain way. And we give them tailored to exactly what they want. Okay, so 3 things: data, analytics, and then the presentation of the data in a very tailored and flexible way. Then you have a chance of optimization. Yeah.
You talk about DSO and having DSO instead of availability. And my question is that why after these all years, we still don't have ISO for all the USs? Just have 7 ISO, why we don't have for all the state? What's the reason of that? So maybe we will have that one again for DSO.
Well, you know, a lot of these things are a function of policy, right? And where I live in the southeast, there's no independent system operator because there's a tremendous backlash from Southern Company who feels that they are the ISO. Okay, so there's a lot of politics that go on with respect in the different regions of the U.S. in terms of having an ISO or not having an ISO. So it's not technical. It's driven by you know, the utilities that are there, the size of those utilities, and what their preference is, and what they want. So that's why there's no ISO in the southeast of the United States. So you'd have to somehow bring some of these utilities together, which is a real challenge to work together. Okay. Yeah. Anybody else?
Other questions? There will be a session at 3:15 in 257. So if you're a student and if you have questions from John, feel free to stop by. It's going to be a 1-hour session. You can ask questions about your career and making decisions as you're graduating. Please join me in thanking John.